session of today and the last session of John. So I think you can do before lecture and then lab. That's all right. The plan is to finish by 6:30, 6:45. So please, John, go ahead.
Hi everyone, can you hear me?
Yes.
Okay. Okay, so I'm going to continue from where we left off before. So I'll first review the parts of the previous lecture that are relevant to what I'm going to talk about today. So remember that we introduced the episodic setting of reinforcement learning, and then first we talked about derivative-free optimization algorithms, including this cross-entry method that was very simple. And then we started to talk about gradient estimation. And we introduced this general technique called the score function gradient estimator. And then we showed how that estimator can be used in the reinforcement learning setting to get this policy gradient estimator. So I'll just review what the policy gradient estimator is. And then we're going to talk a bit more about the policy gradient estimator, because policy gradient methods are actually a very powerful method, and you can apply them to pretty much any kind of problem where you're trying to optimize a policy. But when you just implement the most naive version, it doesn't work very well. It's very inefficient. So there are several modifications that end up making it much more practical. So that's what I'm mainly going to talk about today. I'm going to talk about how to make policy gradient methods better, and in particular using variance reduction to make them work better. So here's just reviewing from yesterday the process that's used to generate a trajectory. And this is just sort of the definition of the episodic reinforcement learning problem. So tau denotes the trajectory, and it's a sequence of states, actions, and rewards. The first state is sampled from this initial state distribution view. Then the action is sampled from the policy, which gives you a distribution over actions given the state. And then you sample the next state and the reward using the dynamics, which is represented by P. This is a probability distribution. And then this continues until you reach a terminal state, which is S sub t here. And then the episode is done. And what we care about is maximizing the expected total reward, which will be denoted by capital R here. And in general, we'll be talking about parameterized policies. So that means that the set of policies is indexed by this parameter vector, theta, which is just a vector of real numbers. And so this just becomes an optimization problem over this vector theta. So yesterday we introduced this very general idea for estimating gradients of expectations called the score function gradient estimator, where, that equal sign is not supposed to be there. So gradient of expectation equals the expectation of grad log probability times the function value. So that means to compute this, all you have to do is take a bunch of samples of x, sampled from your probability distribution B, and then you multiply each of those samples by grad log probability. This assumes that you have access to the probability distribution, and then you average those estimators together, and your sample average gives you an estimate of the gradient. Okay, and then we showed that just directly applying this formula to the probability distribution over trajectories gives you a nice formula for the policy gradient, which is just the gradient of the performance of a policy with respect to the policy parameters. So we're computing the gradient with respect to the policy parameters of expectation over trajectories of total reward, and that ends up being you sum over all time steps of the trajectory, that's t, and you have grad log probability of the action, times this expression, which is sum of future rewards, so that those are all the rewards you receive after the action, minus some baseline. And we had to do a little work with manipulating these expectations to get from this formula to this formula, but it was fairly straightforward. And the interpretation of this formula is, so you have this quantity inside the expectation, which is the policy gradient estimate you get from a single trajectory. And if you move in that direction in parameter space, that means that you're increasing the probability of the good actions and decreasing the probabilities of the bad actions. At least that's what you want to do, and that's what that's the intuition between all of these score function gradient estimation methods. You're collecting samples, and then you're increasing the probability of the good samples and decreasing the probability of the bad samples. And the way that corresponds to this formula inside the expectation is, well, here's the probability of the action at time t, log probability, and then this expression tells you if that action was better or worse than average, because we're looking at all the rewards that happened after that action, and then we're going to subtract this baseline function, which is going to, I'll talk about that a bit later, but that's going to basically approximate what the expected rewards should be starting from that state. So that's telling you what's the average result from that state, and so that's the baseline term on the right, and then this sum term on the left is what happened this time. And if this sum of rewards is really large, that means this action was probably really good. And I'll explain that a little more formally in a moment. Okay, but this is an unbiased estimator for the policy gradient. That's the key thing. But on the other hand, it still has very high variance. So if you go and compute this term inside the expectation, it has the right expectation, but it has very high variance. So it might take way too many samples. John?
Yeah. Just so this baseline, the
Yeah.
condition for this baseline that it's legal to put it there and doesn't change the expectation is that it's just to be independent of theta, right?
It has to.
It has to not depend on theta. So anything that you compare that is independent of theta doesn't change the value of the right-hand side, right?
Right, it can't depend on data. It can depend on any variables that are sampled before action sub t. So if it depends on, so you can put states of S sub 1 in there and S sub 2, whatever you want, as long as, but if you put S sub t plus 1 in there, then it's not right anymore. Because then it might, I mean, when you see the derivation for it, it sort of is clear why that's the case, but it's, let's see, I don't have a super quick explanation of that off the top of it.
Is sometimes interesting to make the baseline depend on the rewards also?
Yeah, you could also make it depend on the past rewards. You can make it depend on all the rewards up to time t. But because of the Markov property, the assumption is that that S sub t captures everything about the history. So I haven't really explained or justified why. Well, I haven't said what this baseline should be. I've just told you that I've just told you that it can be anything, and your estimator is still unbiased. And I told you that you want to sort of subtract out the expectation of this sum of rewards, but I wasn't very precise about it, so I'll be more precise about it shortly. Okay. So to do that, I'll first need to introduce this idea of a value function. So value functions are one of the most important concepts in reinforcement learning. And in fact, many introductions to reinforcement learning start with value functions and start with algorithms that try to solve for the value function. But they sort of play a supporting role here in policy gradient methods, as opposed to a main role. And here they're going to be used for variance reduction. So first we're going to define this state value function. So that tells you the goodness of a state. And formally it's just defined as the expected sum of rewards, given that your first state is S. So value of S is just the expected sum of rewards, given that the first state is S. Okay, and then there's another kind of value function called the state action value function, often called the Q function, which also conditions on the first action. So it's defined as the expected sum of rewards conditioning on the first state and the first action. And this tells you how good is this state and this action. And lastly, we can define this advantage function, which takes the difference between the Q function and the value function. And it tells you how much better is this action A than what the policy pi would have done otherwise. So note that all these functions depend on the current policy pi. So the Q function tells you what's my return going to be if I take action A at the first time step, and then I just follow the policy for all future time steps. So the advantage function says, what happens if I take action A and then I follow the policy for all the future time steps? Is that better or worse than average? Any questions?
Sorry. Here you are not using discounted factors. So
Right.
Are you assuming that there's always something like is always capital T here?
Oh yeah, I've been a little imprecise about that. So I'm assuming in this episodic setting that the expected sum of rewards is always finite. Just let's assume that the expected sum of rewards is always finite. Now, I'm not assuming that the number of time steps is always the same. But it actually doesn't matter, because you can say that actually there's always an infinite number of time steps, but you always reach a terminal state after a finite amount of time, and then you get stuck there. So that way you don't have to worry about if I change my probabilities, how does the length of the trajectory change? So you can say that the length of the trajectory is always infinite, but after a finite amount of time, we reach this terminal state. And this can be defined formally in terms of the Markov chain. Say that this is your stationary distribution. Then we're going to introduce discounts later. Yeah, so I'll introduce those later, but not as part of the MVP definition, but as a variance reduction parameter. Okay, so now we're going to go back to our policy gradient formula and look at how value functions can be used. So this is just the formula we had before, grad log probability times sum of rewards minus baseline. And then we can just move the expectations around a little bit. So here we just move the sum over time outside of the expectation. And here here we did something a little trickier. So here we have, we can consider the variables, all the variables of the trajectory being sampled sequentially. So we can just consider some ordering of the variables, state, action, reward, and so on. And we're going to split up the expectation into two parts. First, we take the expectation over all variables that happen before action sub t. And then inside of that, we take all the variables that happen after action sub t. This is just, we're just using the law of iterated expectations to break up the expectation. And obviously we can pull this term out of the, this term doesn't depend on any of those variables from the future. So this is just, we just move the expectations around. And then, let's see, what did we do here? That looks exactly the same. So, is it exactly the same? Yeah, okay, I probably meant to put something different here, but I messed it up. But anyway, let's see. Oh, okay, next, okay, so forget about this last formula, but the point I was trying to get at is, okay, pretend the baseline isn't there, right? So the point is that the expectation overall of these future random variables of the sum of rewards is the Q function. That's just the definition of the Q function. Yeah, just pretend this B isn't there. So expectation of the sum of future rewards is just conditioned on the state S sub t and A sub t. That's just the Q function by definition. We've written it a little bit differently because we're starting at time t, but because the probabilities are assumed to be stationary over time, it's the same. So that way, so just taking this formula that we had here and just substituting in the Q function instead of just basically taking this expectation and turning it into the Q function, we get this formula for the policy gradient. So now, instead of looking at an actual empirical sum of future rewards, we're just using the Q function. Mm-hmm.
Is it because you now remove the expectation, like in the previous formula you had the expectation of the sum of the rewards minus the baseline, but the baseline is on these, so you take basically out the expectation here, right? I mean, it's not a variable.
Right. Well, the baseline, so S sub t is a random variable, so this this term right here is a random variable, but basically all I did here is I took the reward part, the expression involving a sum of rewards, and I replaced that by its expectation. So I just replaced, so this first part involving the sum, I just replaced that by the Q function. Does that make sense? Any other questions? Okay, so that's our new formula, and well, first let's just look at that formula for a second. So this grad log probability term has expectation 0, so I made that point yesterday. It's pretty simple to derive. You can see that because when you write down the formula for the score function gradient estimator, this grad log. You get grad log probability by just taking the gradient of the expectation of 1. So if you write down grad of expectation of 1, and then you apply the score function gradient estimation formula, you just get the gradient, expectation of grad log probability. Okay, anyway, I'm just saying, my point here is just that this grad log probability term, this has expectation 0. And then I'm going to claim, without any justification, that we also want this term to have expectation 0 in order to reduce variance. Because if it had some non-zero expectation, then we're sort of we're adding a term. I don't know. You can show this formally. I don't have a great intuitive explanation of that, but my best intuitive explanation is that we want to increase the probability of the good actions and decrease the probability of the bad ones. So that means that this expression here should be positive whenever it's a good action, right? Because we're going to try to increase the probability of this action, A sub t, if this expression right here is positive. So we want this thing to be positive whenever it's a good action. So that means, so if we take the baseline to be the state value function, then we get the advantage function here, because that's the Q function minus the B function. And then, and the advantage function tells you if this action was good or bad. So basically with this choice of baseline, we're increasing the probability of the good actions. So that's my justification for why the baseline should be the value function. There's also, you can actually show this formally, so this paper actually goes and computes the variance of the estimator, and it shows that this choice of baseline, it's actually not optimal, it's near optimal. There's actually an even better choice, but it's such a minor improvement, and it's more complicated, so it's not worth talking about too much. Okay, and yeah, so that's the intuition, increase the probability of good actions. So here's our policy gradient formula, and this is sort of the gold standard policy gradient formula, meaning that if we knew what the advantage function was, then this is the formula we would want to use. Unfortunately, we don't know what the advantage function is, so we have to come up with some noisy estimate of the advantage at time t. And that's basically what the subsequent analysis is going to do. It's going to talk about how to estimate the advantage function and then plug it in here. Okay, so this advantage function is not known, but if we plug in a random variable a hat, which we're going to call the advantage estimator, then under certain conditions this is going to be an unbiased estimator of the policy gradient. But as it turns out, we don't even care that much if it's unbiased, because we're going to try to make a bias variance trade-off, and we also care a lot about variance. So we're going to be willing to substitute in biased estimates of the advantage function if we think they're going to be good estimates. So in fact, we've already showed one way of doing this, one estimator for the advantage function. So previously we said you should use the sum of future rewards minus this baseline. And we showed that that gives you an unbiased policy gradient estimator. And if you take the baseline to be some approximation or some estimate of the state value function, then that gives you good variance reduction. So this is our first advantage estimator. But we can try to do a little bit better than this. Okay, so I'm going to talk about how we can do better than that. But first I want to talk about a really general issue in reinforcement learning, which is the delayed reward problem. So in reinforcement learning, you're performing a series of actions, and then there are a series of states and rewards. And the thing that makes it it's different than most problems in supervised learning is that when you perform an action, you have no idea if this action was any good. Because maybe this action was really good, but the good effect only happened way far in the future. Or it might have been really bad because there's some really bad delayed effect to this action. So in reinforcement, so this is usually called the delayed reward problem or the distal reward problem. This just makes it really hard to, RL algorithm, this sort of manifests itself in different ways in different reinforcement learning algorithms, and it's kind of unavoidable. So here's a sort of illustration of that. So you can imagine what's the expected reward over time following different actions you might take. So let's say one action is to smoke crack, and then that's this blue curve, so you're really happy for a short amount of time, and then it's not so good for a while, and then maybe you return to normal. Or you could go to school, which is maybe kind of boring for a while, but maybe it pays off in years down the road because you get a good education, and then you get a good job and live a happy life. So you can. So the problem is that what you really care about is this long-term expected reward, but the effect is just so delayed that it's just really hard to account for it. And this is actually a kind of fundamental problem. I mean, it's also, humans don't seem to solve this perfectly anyway, so because people do things that are they do things that make them happy in the short term, but then make them sad in the long run. So people aren't that good at this, but at least we're not that bad most of the time. So the question is, how do we want to do as well as possible at accounting for delayed rewards? Okay, so how does this manifest itself in policy gradient methods? With policy gradient methods, the issue is that we're mixing together the effect of many actions. So here's the advantage estimator we were using before. So we're estimating the advantage of action, the action at time t, by taking the sum of all future rewards and subtracting out this baseline. So note that this sum of future rewards, it depends on a lot of different actions. It's not just the action we're trying to compute the advantage of. So it depends on the action at time t plus 1, t plus 2. We're mixing these all together. So let's say action sub t plus 1 was really good. Then, and that caused this sum of rewards to be really high. Well then, since we're computing this as the advantage for time t, we're going to think the action at time t was really good. But there's no reason to think that it was good. So since we're mixing together all these effects, we're kind of losing information. And that's unavoidable. So roughly speaking, the signal and noise ratio, when you compute this advantage estimator, scales something like 1 over the time horizon. Or that means, I don't know exactly how it scales, but it gets worse as the time horizon gets longer. And that's because only the action at time t contributes to the signal, but all these future actions contribute to the noise. Because the signal, this is the expectation we're trying to compute, but all these other actions contribute to the estimator, meaning that they're contributing to the variance. Okay, so now I'm going to talk about two different ideas for reducing the variance. And both of them center around just ignoring long-term dependencies, because that's in a certain sense the best thing you can do, though there are better and worse ways to do that. So the first way to do this is to introduce a discount factor. So a discount factor is a real number between 0 and 1. Usually it's closer to 1, so you might see 0.99 or 0.98 or 0.9. And the discount factor downweights the effect of actions that are far in the future, or rewards that are far in the future. So it basically says, let's ignore, when we're planning for our next action, or when we're choosing our next action, let's just pretend that it's not going to affect any rewards far in the future. So we're ignoring long-term dependencies. We can form a different advantage estimator that uses this discounted return, that computes a discounted version of the return instead of the normal return. So now we're gonna take the for the reward 2 time steps in the future, we're gonna multiply by gamma squared. So basically the reward is going to decay over time. And so if gamma equals 0.99, then after 100 time steps, we're multiplying by about 1 over e, and so on. So it's exponentially decreasing the effect of all these rewards. So this obviously reduces to our previous estimator when gamma equals 1. And the idea here is that the advantage, when you introduce this discount factor, if most of the effect happens near to the action, so if most of the effect is not far in the future, it's close, then this should actually be close to the advantage that we actually care about, which is the one we get with gamma equals 1. Okay, we want the advantage function to have expectation 0 as before, so that it measures whether the action was better or worse than average. So we should set the baseline a little differently than we did before. Now we should set the baseline function to be the expectation of the discounted sum of rewards instead of just the regular old sum of rewards. So that way this thing is going to have expectation 0. And actually that's really important when you have a really long time, a large number of time steps, because otherwise this value function might grow without bounds, and then it's going to be really hard to approximate. So if your discount gamma equals 1, and you have thousands or millions of time steps, then the value function is just going to be huge, and it's going to be just really hard to estimate and really hard for your function approximator to get accurately. So actually using a discount is extremely important, and basically everyone uses discounts in any kind of practical reinforcement learning algorithm when you have more than 100 time steps or so. Any questions? Okay, and yeah, this is a bias estimating advantage function. Okay. Let's see. Okay, so that's one approach, and now here's another approach. So the other approach is, instead of just downweighting the future rewards, let's use our value function to try to estimate them. So this is like we're integrating out the future rewards with the help of the value function, instead of just computing them with Monte Carlo. So here's the empirical sum of rewards, which we would usually plug into our advantage estimator. What if, instead of using this formula, we just cut it off after one time step, which effectively integrates out all of the randomness that occurs after that time step. So instead of computing it by Monte Carlo. So we can cut it off after one time step, or we can cut it off after two time steps, or three, and so on. So this is just looking at a fixed time horizon where we take the empirical sum of returns for some number of time steps, and then we just cut off that sum using the value function. With this kind of estimator, we can introduce our baseline again, and we should use the value function as the baseline so that our advantage estimators have mean 0. And then we get advantage estimators that look like this. So let's just look at what this means intuitively. So this is R sub t plus b of s sub t plus 1. This is the estimate of the return using a one-step look ahead. So it's saying over this is the estimate of the return after you reach state s sub t plus 1 and you stop. So if you're just looking one time step into the future, this is what you're seeing, and this is the expected return just starting from time s sub t. I mean state s sub t. So this formula is telling you did our total returns get better or worse over that time step? Because let's say this was a really lucky, really good time step, then the estimate of the returns after that time step is going to be much bigger than the estimate of the returns before it. Like let's say we luckily jumped to some good state, then this part is going to be bigger than this part. So this is telling you, did things get better after the first time step? And then we can do the same thing here. This is measuring whether things got better after the first two time steps, and so on. So you can see why these would potentially be why these would have much lower variance than our estimator that just looks at the whole empirical reward, because this only has one random variable in it. Well, it has two because the state is random and the reward is random, but there's only the amount of randomness doesn't scale with the total number of time steps. It's just basically O of 1. It's just a constant amount of randomness in this formula, this first formula here. So these formulas have much higher, much lower variance. Unfortunately, they have bias. And you can see that, like imagine if your value function v of s sub t plus 1 equals 0, then you're just ignoring all the future rewards. So, yeah.
So when you talk about looking ahead 1 or 2 time steps, all of this is offline learning. So
Well,
you have the whole this and that.
yeah, this can be computed offline after you get the whole trajectory. So I'm assuming here that you collected your whole one trajectory or many trajectories, and then you went back over all the data and you're computing all of these quantities. You can also compute it online, and that's just a matter of doing the right bookkeeping. So you can do the policy grade, you can do all these algorithms fully online, where you don't, there's like a small amount of memory. I mean, that's just equal to the number of parameters. Any other questions?
you have the future reward because you run through this trajectory, why would you want to substitute in an estimate of that?
Right, good question. So it's to reduce the variance because this sum of future rewards depends on also the future actions. So this is going to have variance that grows as the time horizon. So this is going to become a worse and worse. This is going to become a really bad estimate of whether the action at time t was good or not, which is what you're trying to get. So because you're, you have this one rewards. You have this giant series of rewards, and they depend on lots and lots of actions. And you only care about, you're looking at the tiny effect on that sum from one action. So the signal and noise ratio is really low. And whereas if you use this formula, well, if this is actually correct, and this is the correct value function, then you're getting a really good estimate of whether your action was any good. In fact, if you have deterministic dynamics, this is going to be a zero variance estimate. It's going to be a perfect estimate of whether of the advantage. This formula, if v happens to equal v pi, the correct state value function, and if the dynamics are deterministic, then this first formula gives you the exact advantage function with zero variance. So it's all about variance.
Is there people trying to combine somehow these estimators? For example, you could imagine that you run your empirical results for k tags and do empirical lots. Perhaps some of them are going to deal with incremental loss functions given by your conservative estimator. Maybe there's a way where you can have a little bit gain a little bit from both.
Yeah, I think that makes a lot of sense. So the question is, can you, well, if I understood correctly, what if you have all the data so you can compute any of these estimates. You can compute all of them, and then maybe you can look at them and try to infer which one is the best to use. Does anyone try to do that? So I think that makes a lot of sense. Especially if you have, if you have uncertainty on your value function, then that would be especially sensible. I don't know if anyone who's tried this. I've tried something a little similar where I compute a bunch of different estimators, and then I do a training test split and try to figure out which one has a better, where the training the training set gives you when you get the same estimate on both splits. If you get the same gradient estimate on both splits, then that sort of indicates that it's a good estimate. So I've tried, after getting a whole batch of data, to look at the training test split, I couldn't get it to work that well, but I think something like that might work. There's another question?
Yeah, I got a question regarding the previous technique, discounting factors. There we had exponentially decaying factors, like the way it was gamma to the power of some power. Can we use polynomially decreasing factors, like gamma over some power of n?
Yeah. Oh yeah, that's a good question. So the previous slide used an exponentially decaying factor in front of the rewards. So maybe that's too harsh in getting rid of the future rewards. So what if you use some kind of polynomial in time instead? Like you do 1 over t cubed, something like that. So this is actually called hyperbolic discounting, and it's actually been proposed as a model of human behavior because it seems like people don't really use, seem to actually use exponential discounting like this. If you say, you can do experiments with people where you say, would you rather have $1 tomorrow or $2 next week or $3 in a month and so on. You give people all these questions and then you can sort of try to estimate their discount factor because if they have if their discount factor is 1, then they should not care about how far in the future it is. But if they have a really discount factor of it has to be measured in time. But if their discount factor is decaying their preferences really fast, you might expect that they would rather have $1 today rather than $2 tomorrow. So you can measure people's discount factors, and it doesn't seem to actually be exponential. It seems to be more like a polynomial. I don't know if people have seriously attempted this in reinforcement learning. You can try it. It might be interesting. Okay, so we can actually combine these two ideas of discount factors and of cutting off the reward series early by using our value function to integrate out future rewards. So here's just one example of, I mean, this is kind of the stupidest way of combining it, but this is a formula that comes up a lot. So if you have a discount factor, you can take reward plus discount times future value minus the current value. So here you're using a discount factor and you're cutting it off. I mean, why would you want to use the discount factor if you're also cutting off the reward series? Because the discount, I mean, it seems like the discount factor isn't doing very much here, right? Because it's only like making a tiny difference to the value function would be if your discount factor is, say, 0.99. Well, the reason is that the value function is, you don't want the value function to be huge, and it's going to be huge if your discount factor is 1. So if you use a discount factor of 0.99, then you're only summing over about 100 rewards, and you have a reasonably sized, your value function is of a reasonable scale. And this formula will give you, this will be an estimate of the advantage function this will be an approximation of, of this discounted advantage function. So if you consider this formula, and now you want to cut off all the future rewards in this formula, you can replace this sum of all rewards starting at t plus 1 with the value function. And then you get this formula right here. So this formula has been used a lot, and this is what's called an actor-critic method. And the reason it's called that is the policy is referred to as the actor, and the value function is the critic. Because it's sort of saying if the actor did the right thing or not. Okay, so I don't want to go into the full details of this because it's just a kind of hairy derivation, and it's not, well, it's a kind of straightforward derivation, but it's kind of hairy, and no one wants to watch like several slides of math on the slide up here. So I'll just show you the formula, and I'll refer you to the paper if you're interested. So we can actually derive a pretty neat estimator that where everything we've talked about so far is a special case of it. So what we do is we first define this term delta, which is this, which looks at this this difference of reward plus next value minus current value. This depends on gamma, of course, but I'm just going to omit the gamma. But delta depends on gamma. So delta measures whether your discounted return got better or worse over that time step. That's the interpretation of delta. And then we can take a discounted sum of these terms delta. And so that's effectively measuring did your returns get better or worse at time 0, time 1, time 2, and so on. The reason we take that sum is because when we just use the first term in the sum, that turns out to, well, that has really low variance, but it turns out to have high bias. And then we add them, but when we add in more terms, it ends up having lower bias. So, well, I haven't explained this at all, but I just want to say what the formula looks like. As it turns out, this formula interpolates between all the estimators we've reduced before when you change lambda. So when lambda equals 0, then it ends up just being this one-step estimate of return, which has low variance and high bias. And when we set lambda equals 1, it takes the full estimate of return, which has low bias but high variance. So this basically has two parameters, lambda and gamma. Any questions?
No, yeah. Maybe it doesn't make a lot of sense. Okay.
So by AT, the estimator, you're trying to optimize, to find a strategy when you're at a certain state, and you want to find an action that improves your return at that state. And then you maximize based on that estimator. When you maximize, the value function is estimated over a policy P. And when you are maximizing, you are not changing that policy, no? So it's like kind of a myopic, to say so, maximizing strategy. That's the case? Is that
Let's see. I didn't understand the last part.
So you're trying to find an action that improves your reward given a certain state. And when you are maximizing that, you are taking this, you have a policy that is fixed, or do you change in that policy, you are considering the action you are optimizing with, can't actually change the policy.
I see. Okay, yeah. Okay, I understand the question. So the question is, okay, we've been just talking about how to compute the advantage function, but this only makes sense for a fixed, for our current fixed policy, which we use to collect the data, and so it tells you something about our current policy, but then we're going to use this to update the policy. So are we accounting for how the policy is going to change? Because maybe if the policy changes, then all these advantage functions and so forth are just garbage, right?
So the policy is dependent on the action that you are optimizing.
No? The policy depends on...
the policy depends on the action which you are optimizing on. You are trying to find the action that maximizes your reward.
Right, you're trying to, you're trying to change the policy so that you're, in order to maximize reward, and that means you're changing the action distribution. And, the point is, this is just, basically all of this work we're doing right here is to try to get a better estimate of the gradient. So this is just this is like an infinitesimal kind of calculation, in that we only care about what's going on locally around our current policy. So we're just going to compute what direction in policy space is going to improve the policy, and we're just going to make an infinitesimal change to the policy in that direction. Actually, I'll talk a little bit later about what happens if you make a big change to the policy, and can we say anything about how big the step should be. I don't know if I answered your question, but if I didn't, then we can just talk about it after the break in 10 minutes. Any other questions?
In the previous slide, you said that by using the value function, you eliminate the variance that the other actions produce.
Yeah.
So I don't clearly understand how do you compute the value function so that it doesn't incorporate the other actions?
Oh yeah. So the value function is some function that you've okay, yeah, that's a good question. So I didn't explain what this value function comes from. I just said we've got a value function which approximates v pi. So actually, the assumption is that the value function was fit before we did any of this stuff with the policy gradient. So the value function, for now, let's just assume that the value function was fit on a totally different batch of data to try to estimate expected return from any given state. So it's sort of simplest to think about in that case. So let's just pretend the value function was fit on a totally different batch of data. Then, when we use it as a baseline, it's not going to introduce any bias.
So you previously trained it in a supervised manner?
Oh yeah, it's a regression problem, yeah, because it's just trying to measure it's trying to estimate an expectation, so it's just a regression problem. So let's just say that before we did any of this policy update stuff, we tried to solve a nonlinear regression problem to get the value function. Yeah, in fact, if you use the same batch of data to fit the value function and then use that value function for the policy update, then you introduce a little bit of bias, but it doesn't actually matter in most cases. Okay, so that's how you combine these methods, and this. Oh, I was going to have a citation, but I'll have it on a later slide. So this is so my colleagues and I wrote a paper. And called this generalized advantage estimation. So I'll have a citation on the latest paper. Okay, so I just want to mention that there's another totally different approach for doing this. There's another approach for computing policy gradients, which is worth mentioning here, and is quite different from what we've been doing so far. So let's assume that the problem has a continuous action space. So the action is a vector of real numbers. So then we actually, we don't have to just sample an action and then try to increase its probability if it was good. That's what we've been doing, and that's the best we could do before. But actually, if we have a continuous action space, then it makes sense to take a derivative of the Q function. And that tells us what direction in action space is going to make the action better. So the point is that if we have a continuous action, then we can make a different kind of estimator that actually looks at the derivative of the Q function with respect to the action. So you can say that this is if you're familiar with recent results involved in generative models, there is this idea introduced of the reparameterization trick. If you've heard of variational autoencoders, that was this trick that makes it easier to train some generative models. But it's basically the same. We're doing the same thing here. We're reparameterizing the problem so that we actually write the action as a deterministic function of the state input and then some noise. So instead of just saying it's sampled from some probability distribution, we're going to say that we first sample the noise from some fixed distribution and then pass the state and the noise through this deterministic function. And when we write down the action that way, we can differentiate with respect to the parameter of the policy. So we can compute, that way we can compute the derivative of the Q function with respect to the policy parameters. So I won't go into too many details, I just wanted to mention the high level idea and say that there's another approach to policy gradient estimation. And you end up with a formula like this where, I should have had an expectation outside of this sum. But the expectation of the policy gradient ends up being, you take, for the policy, the gradient of the expectation is expectation of a sum over all time of the gradient of the Q value at each time step. So just to say again, this should be in an expectation, this right-hand side. Okay, and this method is called the deterministic policy gradient. Well, it has there's various versions of this. So there's the deterministic policy gradient algorithm, and then there's another one called, there's this other paper that I like where they call it stochastic value gradients, and they look at either learning a Q function or learning a value function and dynamics model, and you get the deterministic policy gradient as one special case of this, but you can also have various other versions of it. So I would say that these methods end up, if they work, if you have the proper Q function, then you can get a really low variance estimate of the policy gradient. Unfortunately, they have a lot of bias, and the bias is usually a lot worse than any of the other methods I've been talking about. So, and it's also kind of dependent on the Q function being smooth. So, so it's sort of an open question exactly which kind of method is going to work better in the long run, or yeah, if these which methods will end up being better. Okay, so actually that's it for this section of the lecture. So I have I made up a practical exercise. So this stuff is kind of complicated to implement, and it usually would take much longer than an hour to get it working from scratch. And some of you, it also requires libraries, like there's a neural network involved. It doesn't work when you just use everything being linear like before, so I have to use a neural network. So that means there are libraries involved, so I thought it would be easier if I just give you some working code and then suggest some different things that you might want to do to modify this code to make it work on other problems or make it work better. So Let me just open it up so you can see, so I can show you what's going on. Let's see. Oh, let's see. There's a link. Well, I'll just show you my local version of it. Okay, so if you go to you have a link to the website, presumably it's on the MLSS webpage. If it's not, I'll just dig it up. But if it's not there, I'll try to find it.
It is.
Okay, it's on the website. Should I just bring up the website? Well, whatever, we can do that later. So anyway, so here's just a description of the problem, and there's some code provided which should work. And if you run this code, let's see if this is going to work. Okay, well, I'm running the code now, and it's just printing out some numbers. Like the relevant one is mean reward, which is the mean total reward of an episode. This is, we're running a policy gradient method here where each iteration you collect a whole bunch of trajectories, and then you, this isn't working very well. Each iteration you collect a whole bunch of trajectories, and then you update the policy to, then you compute a policy gradient estimator, and you take a step in that direction. So you compute trajectories, you collect trajectories, then you compute policy gradient, and then you do an update step in that direction. And this is starting out just on the card pull problem. Actually, someone mentioned it yesterday. I didn't even tell you exactly what it's supposed to look like if you're succeeding. Let me just, there's a line in the code that you can comment or uncomment to make it actually plot what's going on. So let me show you what it looks like. So this is a pole that's supposed to be balanced on this cart, which is the black rectangle, and basically by moving it around you can try to balance it. And if the algorithm works, it should learn how to balance it for a long time. The reward is 1 for every time step that it survives. I think there are 200 time steps max in each episode, so if you're actually succeeding, then you should be able to get a mean reward of 200. So here, it's actually fluctuating wildly if you look at the mean reward. Though sometimes it gets up to about 200. So it should actually converge eventually, but it's fluctuating wildly. This is actually a property of policy gradient methods. It's really hard to get them to actually stably improve. And after this session, I'm going to tell you about how to fix that problem. But this is a well-known problem with policy gradient methods. You would think it would work just fine because you're computing the gradient, and we all know gradient descent works. But the problem is just in reinforcement learning, as you're changing the policy, then your data has totally different statistics, and your step size might be bad. So the problem with this method is it's hard to set a sensible step size. So here it looks like it actually converged after just fluctuating wildly for a long time, and it's managing to survive for the whole allotted 200 time steps. So that seems to have worked. This card pull problem is just a really classic problem in optimal control and reinforcement learning. And it's just used as a test problem. It's not even that good of a test problem, but it's a classic. So let's see. So I'll just mention, okay, you might want to toggle whether you're plotting or not plotting. That's the last line of this learn function. Yeah, there's a bunch of other stuff going on, but hopefully there's some comments, and hopefully those are going to be informative. Yeah. And you might want to change, so what you can do is you can, first of all, you can try to change around the parameters. So here are some parameters. There's this line that says self.config equals blah, blah, blah. So you can try to change all these numbers and see what happens. You can also change the task to basically you can change it to any of the tasks that are in OpenAI Gym. So if I go to this index.html, well, lab 1, if you go back to lab 1, it has a list of several environments that you can use. Like you can use Pendulum. That one has a continuous action space, so you'll have to change the code to run that one. But like Acrobat has a discrete action space, so you should be able to try that one too. So anyway, if you get Carpool working nicely, you can try these other tasks. And I've also suggested a few other things to do. Like, let's see. Oh yeah, so one thing that that sometimes makes this work a lot better is instead of taking a random action, you just take the most likely action. So remember that the policy gradient, we have a stochastic policy, so we have probability of action given state. And the policy gradient formula only makes sense for, it's only training the stochastic policy to be better. But as a sort of hack, we can say, what if we just take the most likely action at every state? And there's absolutely no guarantee that this is going to be any good, but it's usually actually better than the stochastic policy. So that's worth trying. In this case, it's usually much better, and in almost every problem, it's much better. Some problems, it's much worse. Lastly, here's Acrobat is another problem where it's probably not going to work because it's never going to get a reward randomly. So that's because in this Acrobat problem, I'll show you Acrobat. So here what you're trying to do is you're trying to swing, you only control the top, or actually you only control the middle joint. So you're allowed to apply torque at this middle joint, and you're trying to get this thing to swing up so that the bottom tip of the arm goes above this line. So basically what you have to do is pump a bunch of energy into it, so it's swinging back and forth, and then it'll go above this line. But unfortunately with only, I think the default amount of time here is 200 time steps, and unfortunately with 200 time step episodes, it just never randomly gets there, or it's very rare that it randomly gets there. So if you just increase the number of time steps, it'll sometimes randomly succeed, and then that'll help it start learning. So if you want to solve this problem, you can increase the number of time steps. Yeah, so that's Acrobat.
It uses the reward only if it goes above the line, or it can depend on the height it goes.
It's just if it goes above the line. So this is the hard version of the problem. You can make an easier version by giving it a hint that it should try to increase the height. By the way, I didn't show you yesterday because I didn't have a working internet connection, but this library, the gym, is, you can go to gym.openai.com, and that has, that's like our main web page with documentation and everything. This doesn't look like it's working. Okay, but anyway, if you go to that web page, you can find that there are a bunch of different tasks. So you can find the names of all of the MVPs that you can play with, and you can also see what kind of performance other people are seeing on these tasks. Oh, here it is. Okay, so environments. These are the list of tasks. Each environment is like an MVP. Actually, it's a POMVP, meaning it's partially observed. But so you have a list of environments. It's not loading very well, so I won't bother with it. But you can check out the list of environments, and there's also some documentation. So if you get stuck on something, and I'm if you get stuck on something and I'm not, and it's taking a while for me to get to you, you might want to just check out the docs. Yeah, so there are a bunch of different kinds of environments, like control tasks. We have like a fancier physics simulator, but you need a license for that one, unfortunately. We have, but this one is free. We have board games, Atari, algorithmic tasks, like where you have to learn how to add numbers and copy numbers. So that's what we've got. Okay, so Good. So now I'll leave you to work on the problems, and I guess this will, let's, when does my session end? 6:30?
The final thing is 6:45.
6:45. Oh, okay. So actually, let's just take, this is less time than I thought, so why don't you just take like half an hour now to just check out the problem, and then we'll resume the lecture.
Yeah, I think those are good tasks. No, so we might later do something like some training phase or test phase, but we're yeah, that's neat.
No, also the gym
Yeah.
I just started working on or dialogue state.
Oh, cool. Yeah, that's,
But it's no.
you need
Well,
to come up with it, right?
I mean, so one of the things she does this stuff, but really just I'm the mechanic.
Okay.
You literally had like
wow.
doing the job and then people assessing how many jobs you got.
Yeah.
So it's just like finding the job.
Yeah. Oh, wow.
And then they literally just had people agencies that were going and stuff like that.
Yeah.
But it's just also
Yeah. Well, that makes sense. Then you kind of just
well, yeah.
just like process.
No, one thing I was interested in, I mean, you can always add more colors and you have, you know, some sort of functional keyboard. Do you have a discount with respect to like how it's running? Or I guess implicitly.
Not that, no method that like you might be able to compute some kind of estimators.
Yeah, or just rather than just taking the information from what you can take one along with it. See how reward high probability
Right. Reward, I mean, you're answering the reward function or?
yeah, the reward in the future that like makes you get a high it might have a big magnitude, but the variance might be the same size as the magnitude. It might be equal well,
Right. Yeah.
But I guess it's fun.
Yeah, I think we hope to deal with that variance. Yeah,